Okay, so hello and welcome back. Now let's take a look at basically exercise 1.3, which is right over here, and here you want to essentially estimate these operations. For example, they have some essentially addition, multiplication, and subtraction, that sort of thing. And we have learned essentially all of these in the previous section. So now we will do well, actually I'm not going to do any of these. You are going to have to do all of these on your own, and I have essentially given you the solutions for exercise 1.3, so you're good to go. The only thing is that essentially I want to add a few words to what we talked about in the previous videos regarding essentially these exercises, and then you can essentially do all of these on your own. Okay. So the question that we have here is estimate each of the following using the general rule, and essentially the general rule was that, as we talked about it in the previous videos, was that essentially suppose that essentially you want to add a couple of or multiply a couple of numbers together. For example, you have 32,565, and then you multiply it by, for example, 2,563, for example. Okay? Now, if I were to actually follow the general rule, I would have essentially this number is a 4-digit number. This number is a 5-digit number, which means that essentially the largest place value in this number is the thousands place value. In this number is the 10,000s place value. So I will round this number to the 10,000s place value, which is essentially 30,000, and I round this number to the thousands place value. That gives me essentially 3,000. And then when I multiply essentially these numbers together, I get 3 times is equal to 9. And now when you want to multiply, for example, these two numbers together quickly in your head, so what you will do is that basically you see that this number has essentially, apart from the 3 zeros that it has only a 3 basically, and this number essentially it has only a 3 and then a bunch of zeros basically, right? So when you want to do this in your head, you don't care about the number of zeros over here or the number of zeros over here. You keep them as they are, but then the digits that you have to be, of course, multiplied together. So 3 times 3 is equal to 9, right? And then the zeros essentially in both the numbers, meaning that you have to carry over essentially all of these zeros in this number, which is essentially 4 zeros. You put them simply over here, and then the 3 zeros over here, you will put them again over here. You will just add all of the zeros together, right? Meaning that every zero has to be brought simply over here, and you see another 2 zeros. So I bring all of the zeros over here, and then the number becomes a 90 million, right? And the reason why you can do this, you have to, if you don't understand it, now you have all the knowledge that you need in order to essentially prove all of these things to yourself. Meaning that you see over here, if I write essentially a 30,000 times essentially a 3,000, and if I want to multiply them together. So you see over here, a 0 times anything is just a 0, right? Again, a 0 times anything is just basically a bunch of zeros. And of course, you have to essentially put a 0, so I have essentially a 0 times basically these 5 digits. I get 5 digits. Then I put 0 over here, and then multiply this 0 by these 5 digits. I get another 5 digits. Then I put 2 zeros over here, and I multiply this 0 by these 5 digits, so I get another 5 digits. and then I put 1, 2, and then 3 zeros over here, and then I multiply 3 by essentially all of these digits, which is essentially 3 times these 4 zeros, so that gives me essentially 1, 2, 3 and 4 zeros, and then 3 times 3 is equal to 9, right? So you see that essentially now 0, 0, 0, 0, 0, 0, and 0, and a 9. And the number of zeros is essentially 3, 6, and 7. And that's essentially 4 plus 3 is equal to 7. And this 9 is 3 times 3, which is essentially the 9, right? Now you essentially, if you repeat this for any two such numbers, for example, a 20 times, for example, a 3000, right? You would just simply multiply 2 times is equal to 6, and then you have 1, 2, 3, 4 zeros over here. That becomes essentially a 60,000, right? So then when you have essentially a bunch of, for example, some numbers like this, for example, 30,000 times 3,000, then you just simply multiply the 3 by 3, which is a 9, and then you have 4 zeros plus 3 zeros, which is essentially 7 zeros, and that becomes essentially your number. And this calculation, essentially you can do it in your head, right? So then basically your calculation essentially becomes essentially a 30,000 times essentially a 3,000. If I essentially round this number to the greatest place value, and again round this number to the greatest place value respectively, and then the calculation essentially becomes essentially a 9 and 7 zeros, which is essentially a 90 million, right? Now if I do this calculation on my calculator, I will have basically I will have 32,565 times basically 2,563, which is essentially a 83,464,095, right? So it's very close to 83 million. And so then if I want to see essentially how close my estimated number is to the actual number, I will take essentially my number, which is a 90 million, and divide it by 83 million, for example. The rest is not very important. 83 million. But then you see over here that I have to write out essentially all of these zeros. 90 million has essentially 7 zeros, and then this has, I don't know, 6 zeros, or whatever the number of zeros that might be. But you don't have to write out essentially all of these zeros over here, and the reason is that, so you see that if I take this number simply essentially as an 83 million, right? So I have 6 zeros over here, and I want to essentially divide this 90 million and divide it essentially by 83 million, right? So what I can do here is that I can just simply simplify. Essentially I have 6 zeros over here and 6 zeros over here. The 6 zeros I can cancel out with the 6 zeros over here, right? The reason why I can do this is that I can write this calculation as a 90 times essentially a 1 million, which is a 90 million, and that's a 83 times basically times essentially 1 million, right? And then of course I can write the same thing essentially as a 90 over essentially 83 times essentially a 1 million over a 1 million, right? This 1 million times a 1 over a 1 million, 90 over 83. And of course any number divided by itself is just equal to 1, right? So you can cancel the 2 together. The whole thing essentially just becomes a 1. So this whole thing, a 90 million by an 83 million, is just a 90 divided by an 83, right? I can even prove it to you if you want to. Sometimes essentially in a 90 million divided by an 83 million, that's just 1.08, and a 90 divided by an 83 is the same number, 1.08. So then basically you don't have to write out essentially all of these zeros just before entering them into your calculator. Simplify your numbers so that you have the least number of zeros, because that would be unnecessary trouble for you, of course, right? So this gives me essentially 1.08, right? So this gives me essentially a 1.08, which is essentially this number essentially this is actually nothing but essentially a 1 plus a 0.08, right? A 1 is nothing but 100%, right? 100% would be 100%, which is essentially a 1, a number divided by itself. And a 0.08 is the same thing as 8%, right? That's 8%, that's 800th, which is 800th. So that's essentially a 100% plus an 8%, right? So what this means is that, well, this happens because the number in the numerator happened to be larger than the number in the denominator. That was an 90 million, that was an 83 million. So of course 90 million is larger than 83 million, which means that essentially in a 90 million there is an 83 million plus some change, and the change is essentially 88% of 83 million plus essentially the whole 83 million. Okay, so this essentially means that the 90 million is nothing but essentially an 83 million plus essentially 8% of an 83 million, right? So what is 8% of an 83 million? So I write 83 million times basically, I don't know how you write times over here. I write 83 million times basically 8%. 800, that's a 664, that's a 6,640,000, right? So then I said that basically a 90 million is essentially an 83 million plus 8% of 83 million, right? So 8% of 83 million is this number, and if I add to it essentially an 83 million, that's essentially 89,640,000, which is very close to essentially 90 million. And the difference that I get over here is because of the fact that the number that I used over here in order to write out these expressions was a decimal number, and in this decimal number you can see that that's 1.08 433, 734, 939, 76, and these numbers essentially keep going all the way up to infinity. I mean, it keeps going infinitely, because it's a essentially it's an irrational number. Okay. What that means doesn't matter, but what it means is that essentially a 90 is not actually divisible by an 83, which means that you would get essentially all of these digits that just keep going and going and going, which means that you would not get an exact number. And when you use essentially such numbers, then there is going to be essentially this kind of discrepancy, meaning there is this difference of what we got over here. Okay. Now essentially what's important here is that basically that in the approximation that we did over here is that essentially the number that I got, I was supposed to get actually an 83 million. I got a 90 million, and the difference between essentially these two numbers is only essentially, this number is larger than this number only by 8%, right? Only by 8%, right? So that's basically that. Okay. Now let's take a look at these numbers. Let's see if we can actually essentially increase the efficiency of this work by rounding the numbers in a different way. Meaning that, for example, over here what I did was that I rounded essentially this number I rounded to the thousands place value, and this number to the 10,000 place value. Now what I'm going to do is that I'm going to round this number to the same place value, which would be essentially a 30,000, and then I'm going to round this number to the thousands place value this time. See if we can get a closer approximation. So that's a 33,000, right? That's a 32,500, that which becomes essentially 33,000 when you round your number to the thousands place value. And then the number essentially becomes essentially a 30 times 33 is 99, and then you have 3 and 3 zeros, so 6 zeros over here. That's a 99 million. Now if I write essentially a 99 million over here, if I write essentially a 99 million divided by 83 million, that gives me a 1.19. And 99 million by an 83 million. So the 83 million was the actual number that we were supposed to get, right? And we got over here a 99 million. That gives me essentially a 1.19, right? 1.19, which essentially means that there is essentially 1.19 is the same thing as 1 plus 0.19, which is essentially 100% plus a 19%, and you see that essentially over here the difference was actually an 8%, and when I rounded the number to essentially to a smaller place value in this number, the difference between the two numbers got even larger, meaning that from 8% I got to essentially to 19%, right? So it's not always helpful to essentially round your numbers to a smaller place value, but then in some cases of course it's going to be helpful, right? But then as a rule you can take this, meaning that you can take the general rule, which is essentially take every number that you have. For example, you have 32,565 and 2,563, and then you see that essentially the largest place value in this number is the thousandth place value. So round the number to the thousandth place value. You see that the largest place value in this number is the 10,000, so round the number to the 10,000th place value, and then basically you will get these two numbers, multiply them together, and that becomes your approximation. Now if you need a better approximation, sometimes you will get a better approximation by essentially by rounding the numbers to essentially to smaller place values in the numbers. Meaning that, for example, over here I have the 33,000. Let me essentially multiply, let me round this number to the thousandth place value, which gives me essentially a 33,000, and then I will multiply this by, and I will round this to the hundredth place value, which gives me a 2600 times a 2600. Now of course this is not very easy to do, because what is 33 times 26? It's not very easy to do in your head, but just for the sake of this example, 33 times 26 is a 858. That's essentially an 858, and then I have 3 zeros and 2 zeros, so I have 5 zeros over here. That's 85,800,000, and 83, for example, you see over here. So it's very close now. 86 million and 83 million, only 3 million difference. And now if you essentially take your numbers, basically 86 million divided by 83 million, it gives you a 1.03. That means essentially there is only 3% difference between the two numbers, right? So we have to essentially play with these depending on the situation to essentially to get better approximations. Sometimes it doesn't even, you saw that essentially in the second example that I did over here, it got even worse, right? But then when I rounded the numbers essentially again in a different way, of course the calculation got a little bit more difficult, but then essentially I got very close to the actual number, right? So all of these essentially you can take into consideration, and now you can essentially go to exercise 1.3, and I have also given you the solutions which are I've gotten from the tiwariacademy.com. And again, I should point out that essentially in these solutions from the Tiwari Academy, around 1-3% of the time you would get essentially some mistakes over here. So you have to be aware of them. And now you can essentially go through these exercises on your own. And it is absolutely imperative that you do these exercises, okay? Absolutely necessary. And whenever you do mathematics, meaning that, for example, you want to do these exercises, the correct way of doing it so that it essentially sits in your mind and becomes a part of your mind, you will have to have essentially some draft paper and essentially a pen, pencil, something you're comfortable with. And then you will have to write down each and every one of these things, step by step, work through them. And then when you use your hand actually with a pen or a pencil, when you use your hand to write down your mathematics, then your mathematics essentially becomes a part of you. Okay, it doesn't help just to look at things. You have to do it with your hand, meaning you write it down with your hands. And even the exercises and the examples that I do over here on the video, when you watch the video and understand what's going on, then you can just, and you should actually, I would actually pause the video, write down essentially the whole problem and the whole solution, and then move on to the next thing. Okay, it's very important. Otherwise you will just simply, well, most probably I would say 90, 85, 87, 88% probability you will just simply lose all of these things over time. Okay, do it with your hand on a piece of paper. Okay, whatever it is that you want to stay with you. Okay, so that's basically all about exercise 1.3, and then in the next video we will talk about using brackets. Thank you. Okay, so now in this video we will talk about using brackets, and this is essentially the beginning of algebra. I mean, in these sections over here, for example, using brackets and basically expanding brackets, and essentially this is the beginning of algebra, and this is something that you need to essentially to understand about essentially the books that I have, these books that I have chosen for essentially for these courses. They do this job very skillfully of teaching you, well, everything that is about mathematics, and they have put the right thing in the right place. You just need to essentially understand everything that is presented here, and then it's like building essentially building the foundations of something great, but then essentially you build the foundations essentially bit by bit, and then you keep building upon essentially those little foundations, and then over time you will have essentially this great, basically this great foundation and everything of mathematics essentially built on top of essentially one another. And so then over time you're going to be a master of mathematics in your own right, of course. But everything that I present over here, you need to understand it before moving essentially to the next thing. If there is something that you don't understand, you can always ask questions, and then I mean, everything that is presented here, you need to be able to understand it properly. Meaning that, for example, when I say that, for example, a 33,000, for example, times a 3,000, I did this in the previous video. When I say that you want to do this operation, so you would multiply essentially all the digits that you find essentially in this number, apart from zeros, which is essentially 33, and all the digits that you find in this number, which is just the 3 apart from the zeros, and then you would have essentially a 33 and a 3. And multiply these together. That's a 3 times 33 is 99, and then you have 6 zeros over here, 3 zeros over here, and 3 zeros over here, and that becomes essentially your calculation, meaning that you don't have to go through essentially long multiplication. You can do this even in your head, right? But when you hear this from me, of course, whenever I say something, I try to, or I actually show you essentially why that is. But if there is something that you don't understand, then you have to ask questions, meaning that essentially when I say that 33,000 times 3,000 is a 99 million, you need to know essentially why I'm saying this. Don't just accept something from me. You need to know the actual reason, okay, and then move to the other thing. And then if you have this kind of attitude throughout all of these courses that we have here, then when you get to calculus, then you will realize and you will see that essentially calculus is nothing but essentially all of these little simple things essentially put together. And then of course it's taken mathematicians maybe 2,000-3,000 years to get to calculus, but then essentially it's not a very, I mean, it's in no way anything complicated. You can, if you understand these simple things, then of course you will understand calculus without any problems. Okay, now let's come back to using brackets, or essentially brackets. So what do you use brackets for? Now suppose that Mira is a name of a person. Mira essentially buys 6 notebooks. She buys 6 notebooks. Essentially each 10 rupees. So that's essentially rupees. You would write it this way, or you could even write, let me make it simpler. Let's say essentially 10 rupees, or essentially $10. So it's just the currency unit for the money that you find in India, basically. So you buy essentially 6 notebooks, each 10 rupees. And then basically her sister Seema buys basically 7 notebooks, and the same amount, essentially each 10 rupees. Now they want to know essentially how much essentially how much they have to pay essentially together, meaning essentially Mira has to pay essentially some amount of money, Seema has to pay some amount of money. Then essentially if they were to essentially to pay the money together, basically not individually but essentially the money together, then how much they would have to pay. Now in order to calculate the amount of money you buy essentially 6 notebooks, and each and 1 notebook essentially costs you 10 rupees. So that means essentially 10 plus 10 plus 10 plus 10 plus 10 plus 10 rupees 6 times, right? That would be essentially 60 rupees, right? Instead of writing 10 plus 10 plus 10 6 times, of course you can use multiplication. So that's essentially 6 times. So then you could use multiplication and say essentially 6 times 10 rupees, that would be essentially 60 rupees, right? That's essentially the same thing. And then basically Seema essentially has to do the exact same thing. She buys essentially 7 notebooks. So 7 notebooks essentially times 10 rupees each, that would be essentially 70 rupees. And this would be 6 times 10 rupees, that would be 60 rupees. So then 60 rupees plus 70 rupees, that would be essentially 130 rupees, right? That's the amount of money that they have to pay essentially together for all the notebooks that they buy, right? Now how do I write this operation? How do I essentially, now I have this expression over here and this expression over here, and I want to put them together. So I can write essentially 6 times 10 rupees, and since essentially I'm adding these together, so I'm going to add to that 7 times 10 rupees, and that would be essentially, then when you want to evaluate this expression in mathematics, essentially we have essentially priorities essentially when it comes to doing these types of operations. When you say essentially 6 times 10, it's very easy, because you know that essentially you just multiply 6 by 10, which is essentially a 60. So there is no confusion there, right? But then when there is this kind of operation over here, then it gets a little bit complicated, because now you don't know essentially where to start, which one. For example, there is 6 times 10 over here, then there is 10 plus a 7 over here, then there is 7 times a 10 over here. Which one should you do first, right? or essentially in what order. So the order that you keep in mathematics is that you will, first of all, you will have to start from left to right. In mathematics, always you will start from left to right. That's rule number one. Rule number two is that you have to essentially take into consideration the priority that each of these operations have. Meaning that essentially multiplication and division have the first priority, and addition and subtraction have the second priority. So when you start from the left, then whenever you see essentially multiplication or division, you will give them the first priority. So this is the first priority, and then again this has the first priority because this is multiplication, and then essentially addition or subtraction has the second priority. So that, which means that essentially you start from left to right. First you will do this one and this one, and then once you have done, essentially this is one, and then once you have done these two, then you will do essentially this second operation over here. And of course then you can imagine that you have to write your expressions based on the same rules, right? Meaning that these priorities and then essentially left to right and everything has to be taken into consideration when you want to write your own expression. Essentially over here you did not write down this expression yourself. You just read, essentially I'm writing this, so I write 6 times 10 plus 7 times 10, and then I will ask you to evaluate this, right? And then when you want to evaluate it, you will say that, okay, so this has the first priority, this has the first priority because both are essentially multiplication, and this has the second priority. So I will write this as, in evaluation, I will write as 6 times 10 is equal to 60 plus 7 times is 70. And now essentially this has, then basically this is the next thing that you will do, and that would be essentially 130, and that's how you evaluate the expression. But this expression you did not write it yourself, you just read it somewhere. I mean, I happened to write it, so you read it essentially in a book or essentially on this video, and then you will evaluate it, right? But then when you want to write down your own expressions yourself, you will have to observe the same rules, meaning that you bought essentially 6 notebooks for 10 rupees, and then again in some other instance basically you buy 7 notebooks for 10 rupees. When you want to write it down, you will write it as 6 times 10 rupees, that's essentially one thing, and then 7 times 10 rupees, that's another thing. And then when you want to put them together, if you put the plus sign over here, keeping those rules in mind, now you know that essentially first this part will be evaluated, then this part will be evaluated, and then the whole thing will be evaluated. So which means that essentially 6 times 10 is equal to 60, 7 times 10 is 70, and then when these two are added together you get 130, which actually corresponds with the total amount of money that you paid. So which means that essentially you have written your whole expression correctly without any problems, right? Now when we get to some better example, I will show you how you could actually mess your own expressions up, how you could mess up your own expressions, meaning that it's possible actually to write something incorrectly, and then when you evaluate it, you will get a completely different answer which doesn't correspond with the, for example, the total amount of money that you happen to pay. Okay, so then basically So then essentially when you want to, when they want to essentially calculate the total amount of money that both of them paid, they could simply write essentially this is 7 times 10, which is equal to 70. So they could write essentially 6 times 10 plus essentially a 7 times 10, and that would be equal to a 60 plus a 70, which is equal to 130, right? So that's one way to write it. Now another way to write down the exact same situation is that I could say that, well, the unit price for the notebooks essentially in both of the situations was the same, meaning that in both the situations essentially a notebook costs essentially 10 rupees, right? So I can essentially first essentially add the number of notebooks together, meaning that I bought essentially 6 notebooks over here, and then I bought basically 7 notebooks over here, and so that's the same thing as essentially 13 notebooks. And then because of the fact that essentially each notebook essentially costs 10 rupees, then I can say that I bought 13 notebooks, and basically each of the notebooks is going to cost 10 rupees. That's going to be essentially 130 rupees, which is essentially the exact same thing that we got over here, right? So this essentially shows us essentially something interesting about algebra, which means that essentially this expression over here is 6 times 10 plus 7 times 10 is actually the same thing as essentially 13 times 10, which is equal to 130. You see, this whole thing is equal to 130. This whole thing is equal to 130, which means that this whole thing must be equal to this whole thing. So this whole thing is equal to this whole thing is equal to 130, right? Now you see over here that essentially in this expression I have a 6 times 10, a 7 times 10 plus sign, and then over here I have a 13 times 10. And you know that essentially 6 plus 7 is equal to 13, right? So a 6 plus a 7 is equal to 13, and then the 10 essentially is being repeated over here, right? Which means that essentially I could say that essentially a 6 times 10 plus a 7 times 10, I can essentially, I have this expression over here plus this expression over here, and essentially both are multiplication, and then they have been added together, right? So then I could say that because of the fact that the 10 is common essentially between the two expressions, I can take the 10 out as a common factor basically, and I can say that this is the same thing as 10 times, it's the same thing as 10 times basically a 6 plus a 7, right? A 6 plus a 7, and it's the same thing as essentially a 10 times basically 6 plus a 7 is equal to 13 is equal to 130, right? So I can write this over here, which means that essentially if I were to generalize this as a rule in algebra, I could say that essentially sum A times basically a C, for example, plus basically a 7, and I put brackets over here so that you can read these properly. Sum B basically times the same C, C and C and C and C. Essentially the C is 10 is equal to 10, right? And I have taken the 6 as the A, and then I have taken the 7 as the B. I can basically, what I can do is that I can, since the C is common, I can take it out and multiply it by essentially A plus the B, right? So A plus the B, right? So then now this is a rule in algebra that you can use everywhere. Well, at least for real numbers, there is no problem. And real numbers is essentially, what I mean by real numbers is essentially any number that you can think of up to now. Later on we will have some other numbers that are not real numbers, for example imaginary numbers or complex numbers, but for now we can, all that we work with is just real numbers basically. So for real numbers, meaning for general numbers 1, 2, 3, 4, 5, 6, even essentially decimal numbers, they are all real numbers, and this rule essentially applies in the case of all of those numbers. So, and of course when you write this expression this way, this automatically means that essentially c times a plus b, meaning this side over here, is of course going to be equal to this side, which is a times c plus b times c. So all I have done is that the same expression, I've written it the other way around. I've brought essentially this side to the left hand side, and the right hand side I've brought it to the and the left hand side I've brought it to the right hand side. Okay. Now there is something interesting that you would notice here as well, and that is when you say essentially c times a plus b, which is equal to a times c plus b times c, you can see that you have multiplication over here, and so this is c times a, right? Or essentially a times c, which is the same thing, because multiplication is commutative, meaning that whether you say essentially a times c or c times a, or essentially c times a, is going to be exactly the same thing. It doesn't matter. Meaning 2 times 5 is equal to 5 times 2. So essentially multiplication is commutative. You can just change the order of the numbers and then the result is going to be the same. So then you can see that essentially c times a, which is a times c, which is the same thing, and over here you can see essentially c times b, or essentially b times c, which is the same thing. So which means that essentially, and then there is the addition sign, which comes over here, right? And the multiplication sign, which is this one, comes over here, right? So then essentially another rule in algebra would be to say that essentially multiplication now I don't remember the exact expression that we use in mathematics. Multiplication basically distributes over addition. Okay, we say multiplication distributes over addition. So multiplication distributes over addition, right? That's the meaning of this expression. Okay, so then what this means, and then there is of course another rule, that is that we say that essentially multiplication distributes even over subtraction, which I will show you essentially in just a few moments basically. Okay, so then in algebra basically now we have a couple of interesting things. First of all, we can say that essentially c times a plus b, c times a plus b, which you can write as c times a plus b, meaning that the multiplication sign, you don't actually have to write it, it's implied. Okay, that's the same thing as essentially, because of the fact that essentially multiplication distributes over addition, then you can say that this is equal to c times a plus basically c times b, which means that essentially you go this way. C times A plus C times B. This is the meaning of essentially the expression multiplication distributes over addition, right? That is one thing. And also the other thing that we talked about here is that essentially you can go the other way around, meaning that when you have essentially C times A plus essentially a C times B, and note that essentially there is addition over here, meaning that this expression is being added to this expression, and essentially there is multiplication and multiplication, meaning that both this expression and this expression have to actually be multiplication. Okay, it's not possible that, for example, one of them is multiplication, the other one is, for example, division. That it doesn't work like that. Okay, but as long as essentially both of these expressions are multiplication and they are being added together, we can factorize the common factor. And factorizing the common factor means that essentially the common factor is a C over here, so the same C is being multiplied by different things essentially in the two parts of this operation. So I will take the C out and multiply it by basically A plus a B, basically, right? Which is essentially the same thing, and instead of writing C times A plus B, you can just simply say C times essentially A plus B, meaning the multiplication sign. You don't have to write it over here, right? So it's the exact same thing. When you have essentially this expression, you can essentially distribute or essentially spread it out and write it as C times A plus basically C times B, right? You can write it this way. Or when you have this expression like what you have over here, you can factorize the common factor and write it as C times A plus B. Okay, and again, one more thing that we learned over here is that basically multiplication is commutative. Commutative, that means that essentially the factors in a multiplication operation, they can commute. Commute means essentially you can swap the values, meaning that essentially instead of saying A times B, you can say to essentially B times A, for example. It's going to be the same thing, meaning that instead of saying 2 times 5, you can say essentially 5 times 2, and 2 times 5 is equal to 10, 5 times 2 is equal to 10, right? So that's another thing that we learned here, right? Now let's now get to essentially let's go back to the same situation that we had over here, that Mira and Seema, they have essentially they bought essentially these notebooks. Okay, we can essentially still talk a little bit about the situation. Now essentially the way that they calculated the total amount of money that they paid together, Seema said that essentially that we had essentially 6 notebooks, each basically 10 rupees, plus 7 notebooks, each 10 rupees, and that would be essentially the right thing to say or to write. And then that would be essentially 6 times 10 is equal to 60, plus, and then 7 times 10 is equal to 70, and that's essentially 130. And this is essentially taking the priority of these operations into consideration, meaning that essentially multiplication and division have the first priority, and then addition has the second priority in evaluating essentially any sort of basic operation like this, right? And then basically it seems that Miraz said that essentially, since the unit price essentially for the notebooks were in both cases were the same, essentially 10 rupees and 10 rupees, I'm going to say that essentially we bought essentially 6 plus 7 basically notebooks, which is 13 notebooks, and then basically 13 notebooks times basically 10 rupees would be essentially 130 rupees. So in both cases essentially they got the right answer, right? Now this is essentially, so this means that essentially this operation over here, 6 plus 7, which is 13, and 13 times 10, so then I could probably even write it as 6 plus 7 times, which is 13, times a 10 basically, right? And that would be essentially, and then that would be essentially 6 plus 7 is 13, and 13 times 10 is equal to 130, which would be the same thing, right? But the problem is that essentially, because of the fact that you have essentially these priorities in essentially in evaluating these expressions, it's not possible to write the exact same thing. It's not possible to write it like this, because if I wrote this essentially over here, this essentially means that because of the fact that multiplication has the first priority, first I'll have to evaluate this part, which means that essentially that is 6 plus, and 7 times 10 is equal to 70, and that becomes essentially a 76, right? But then essentially we didn't pay 76 rupees, we paid essentially 130 rupees. So which means that essentially I mean to talk about this situation over here, but then it seems that essentially I'm talking about something completely different, which means that essentially when you want to write down your own expressions, you have to make sure that essentially that you take those rules of priority into consideration, which means that this is not right, and therefore I need to write essentially a 6 plus 7, which is 13 times a 10. But then if I put a bracket over here, then this essentially becomes essentially this expression. Now this expression that you see over here is exactly the same as this expression that you see over here, except that you have these brackets over here, right? And these brackets are going to take care of the problem because of the fact that essentially you still have the same rules. Essentially you go from left to right, and essentially multiplication and division have the first priority, addition and subtraction have the second priority. But then any sort of bracket that you use in your expression, it's going to take essentially the first priority. Any sort of bracket that you use, it's going to take the first priority, meaning that basically or essentially, and many sorts of brackets you can use in mathematics. You can use parentheses, you can use curly braces, you can use square brackets, and these are usually the 3 types of brackets that we use essentially in mathematics. Now any of these pairs of brackets that you use in your expression, it's going to take the first priority, meaning that whatever there is inside the bracket, you will evaluate it first, and then you will get to the other things, okay? Which means that essentially over here, I'm going to say that essentially first I have to take care of, I'm going to take care of essentially this part, because there is a bracket over here, and then there is the multiplication, which then I'm going to evaluate next basically. So 6 plus 7 is equal to 13 times a 10, which is equal to 130. Okay, so that in this instance basically the bracket essentially comes to our rescue, and basically solves the problem. Okay, so that's essentially what we have here. To avoid confusion in such cases, we may use brackets. We can pack the numbers 6 and 7 together using a bracket, indicating that the pack is to be treated as a single number. Thus the answer is found by essentially this. And so then as a rule, we can say that first turn everything inside the brackets into a simple number, and then do the operation outside, which in this case is to multiply by 10. So essentially what that means is that whenever you have a bracket in your expression, or essentially one pair of bracket, or even more than one pair of brackets, first essentially you have to take care of each and every bracket. Okay, and once you're done with the brackets, then you will get to the rest of your expression, again having the same rules essentially into consideration, meaning that multiplication and division have the first priority, addition and subtraction have the second priority, and of course you have to work your way from left to right basically. Okay, so then basically we will get to these essentially these questions over here. Let me put them on the let me bring them into my sheet, and then we will talk about these as well. Okay, so now the first question that we have here, if I can make this a little bit larger, and okay, so the first question that we have over here is write the expressions for each of the following using brackets. Okay, so you see that over here we have 4 multiplied by the sum of 9 and 2. So essentially 4 multiplied by the sum of 9 and 2. The sum of 9 and 2, essentially sum means addition, right? So the sum of 9 and 2 essentially would be 9 plus 2, right? Now the way that essentially this has been formulated, it means that essentially 4 is going to be multiplied by the sum of 9 and 2. And the sum of 9 and 2 is 11, meaning that 4 is supposed to be multiplied by the 11, which is supposed to be equal to 44, right? But then essentially if I write my expression this way, meaning essentially 4 times 9 plus 2, what this means is that based on the rules of essentially priority and arithmetic, then I will have to, because essentially the multiplication has the first priority, first I'll have to evaluate this part, which is essentially 36, then plus a 2, which is equal to 38. And this is essentially, if I wrote my expression this way, and if I evaluated it this way, it would be, of course, there is nothing wrong with this. The only problem is that this is not the same thing that is meant over here. What is meant over here is that the 4 is supposed to be multiplied by the sum of 9 and 2, which is essentially 11. So then if I put essentially the bracket over here, then I have written down exactly what is meant over here, right? So then I would write this as 4 times essentially 9 plus 2 is equal to 11. And now essentially because of the fact that there is a bracket over here, and the bracket gets the first priority, first I'm going to have to essentially to evaluate the bracket, and then I will have to essentially, then I will evaluate essentially the multiplication sign over here. So then I will write this as 4 times, then this gets the first priority because there is a bracket over here, times 11 is equal to 44. Okay, so that's basically that. Next, basically we have essentially divide the difference of 18 and 6 by 4. you want to divide the difference of 18 and 6. What is the difference of 18 and 6? So that's 18 minus 6. That's the difference of 18 and 6. And you want to divide this by 4. So then divide this whole difference by 4. That's what is meant here, right? Now if I wrote this, and then that would be essentially something like, for example, a 12 and then divided by 4, which is equal to 3, right? So this seems to be easy. There seems to be no problem with this. Now the problem here is that essentially you could also write the same expression, meaning the difference of 18 and 4, which is 18 and 6, which is 18 basically minus 6, and you want to divide this by 4. So divide by 4, right? So then this is of course not the same expression, because over here we are essentially 18 minus 6, whatever this whole thing is, I'm dividing it by 4. But then over here, because essentially division has priority over subtraction, so then first I have to essentially I have to evaluate this part and then subtract the whole thing from an 18, which means that essentially 16 minus 4 is something like 1.2 or so. I'm not even sure what that is. So 6 divided by 4 is the same thing as 3 divided by 2, which is 1.5, right? That's a 1.5. So then I will have to write this as 18 minus, and then evaluate this part first, which is 1.5, and then 18 minus 1.5 is 16.5, right? So over here I get a 16.5, I'll get a 3 over here, and they are supposed to be the same expression, which is, of course, they are not the same expressions. So in order to make them the same expressions, all I need to do is that I put essentially a pair of brackets over here, which means that first I will take the difference of 18 and 6, put it in a bracket, and then divide that by 4. Divide that by 4. So then essentially, since a bracket has priority over anything in an expression, 18 minus 6 is equal to 12, and then divide by 4 is equal to 3, which then essentially is the same thing. So you could write essentially 18 minus 6 divided by 4 is the same thing as essentially 18 minus 6 divided by 4 is equal to 3. Okay, but then the bracket is absolutely necessary here. Otherwise, essentially you would have written essentially a completely different thing with a completely different basically result, basically. Okay. Now the next part of this question is essentially 45 divided by 3 times the sum of 3 and 2. So we have 45 divided by 3 times the sum of 3 and 2. Right? What is that? So you have a 45 divided by 3 times basically times the sum of 3 and 2. The sum of 3 and 2. When you say essentially the sum of 3 and 2, that means 3 plus 2. And then 3 times, when you say times, of course, that means multiplication. And that's essentially the expression that we have. Now, based on what I read here, this is the correct way of basically writing it. And so that's 45 divided by 3 times, and that means that essentially 45 is divided by this whole thing, 3 times the sum of 3 and 2, right? And this would be essentially a 45 divided by 3 times, and then essentially we have the bracket, so that's a 5, so that's a 45 divided by 3 times 5 is equal to 15, and then 3 times 15 is equal to 45, so 45 divided by 15 is equal to 3, right? So that's how you're supposed to write this, right? Now the problem here is again is that you might actually make mistakes essentially over here with the division. For example, I could write essentially a 45 divided by, okay, and then 3 times the sum of 3 and 2. The sum of 3 and 2, you could write it this way, and then just simply not use any brackets over here, right? Now this expression is of course not the same thing, meaning that it's going to return a different result basically. Because essentially when I want to, essentially if you give me this expression, and if I want to essentially evaluate the expression, I would have to start from the left and move towards the right. And then of course you know that multiplication and division have priorities. So then of course I will go with this part, which is 45 divided by 3, which is essentially a 15. And times 3 plus 2, right? Again, I start from the left, go towards the right, and multiplication has the priority. So that's essentially 15 times 3, which is equal to 45, plus a 2, which is equal to 47, right? But then essentially this is not what I was looking for, right? The answer is supposed to be a 3, right? So then what I'm going to do is that I'm going to use essentially the proper brackets this time. I'm going to use the proper brackets. So it says essentially 45 divided by, so the 45 is going to be divided by this whole thing, whatever that is. So this whole thing has to get into a bracket, right? And then essentially over here, this part, we are saying 3 times the sum of 2 and 3 and 2. So that means that essentially this 3 is supposed to be multiplied by this whole sum over here. So I put essentially this sum in a pair of brackets, which means that the 3 is multiplied by this whole thing, right? And then the 45 is then divided by this whole thing over here, right? And then you can essentially evaluate this, meaning that essentially in this expression I have essentially this bracket over here, which is the outer bracket, and then I have this inner bracket, or essentially which is called a nested bracket. A nested bracket. So that's a nested bracket, or essentially we have nesting over here in our brackets, meaning that essentially the inner bracket has been nested in the outer pair of brackets basically. And so then basically whenever you have this kind of situation, you will have to move essentially you will have to move inside all of the brackets, and then the innermost bracket you will evaluate first, and then you come and then you come out one more step, and one more step, and one more step. You keep coming out and you keep evaluating until you get to the outermost brackets basically. So then what I'm going to do is that I'm going to move essentially all the way inside all the brackets, which is essentially this bracket over here. And then I'm going to write it as a 45 divided by 3 times, and then 3 plus 2 is equal to 5, right? Now again I have this bracket over here, which means that I have to evaluate first, and then I can get to division. So that's a 45 divided by a 15, which is equal to 3 basically. The same answer that we got over here. Okay. So these are very important, of course, in arithmetic and of course in algebra. I mean, these are the basics of These are the foundations of algebra. So I mean, right now we are working with them in terms of numbers, but then when you get to algebra, then instead of using essentially these numbers like 7, 5, 3, 2, and so on and so forth, you will use variables like a, b, c, and so on and so forth. Okay, which is of course I mean going through algebra is actually a really exciting journey, and then algebra is like this is like the spirit of mathematics, and then is like the soul of mathematics, and then the soul, essentially through the soul, all the other parts of the mathematics essentially come to life. For example, I don't know, anything that you take in mathematics, for example, I don't know, geometry. When you make geometry a little bit more advanced, and you make essentially, for example, coordinate geometry out of geometry, then you have coordinate geometry, but then the soul of coordinate geometry is still algebra. I don't know, trigonometry. In trigonometry, still you're working essentially with angles, and essentially with you're essentially working with angles. But then again, essentially what makes the whole thing work essentially is still the algebra. The algebra is the soul essentially behind everything that works in trigonometry. And then again, even when you get to calculus, essentially calculus is the soul of calculus basically is again algebra. So essentially over here, what we are doing is that we are essentially working with the basics of algebra. Later on we will make this a little bit more advanced, and then we will essentially create algebra out of this whole thing, and then essentially then we will use algebra in order to give soul essentially to everything else that we do in mathematics, which is a very exciting process, really. Okay, hopefully we can go through the whole thing without problems. Okay, so that was the whole thing, and question number 2 and 3 you can just simply ignore. This is not the right way of asking this question, and later on we will have essentially examples. We will have enough examples essentially to understand these properly. So essentially these two questions you can just simply ignore. Okay, so that's all about this part, so essentially using brackets, and then in the next section we will talk about expanding brackets. Thank you. Okay, so now let's talk about expanding brackets, and of course in expanding brackets you will use essentially the exact same rules that we had before, meaning essentially the order of precedence or the order of priority has to be taken into consideration in whatever you do, meaning that again basically you will essentially always move from left to right in your expression. Number 2, essentially brackets essentially have precedence or basically priority over everything else, meaning over subtraction, multiplication, division and addition. And then basically after brackets, then basically multiplication and division essentially have precedence over over addition and subtraction. So what that means is that essentially in the order of precedence, you have essentially multiplication and basically division, and then the next order of precedence would be addition and subtraction. Okay, so which means that essentially multiplication and division have basically priority over addition and subtraction. Okay, so that's essentially the rules that we have, and essentially usually, I mean, not usually, but I never actually discuss rules about things. I almost never discuss rule about things, but these are essentially conventions, and these are essentially conventions that are supposed to be taken into consideration by everyone, meaning that essentially by convention we have said that essentially when you want to mean, for example, you saw over here that we said that, for example, you want to write this expression 4 multiplied by the sum of 9 and 2. So 4 multiplied by, so you multiply 4 by the sum of 9 and 2, meaning that first you have to essentially take into consideration the sum of 9 and 2, which is 11, for example, and then you will multiply it by 4, right? So essentially the sum has to be calculated first, and then you will multiply it by 4, and this is so because of the fact that that's what I want it to be, right? Meaning that when I say essentially 4, when I say basically 4 multiplied by the sum of, for example, 9 and 2, for example. So what I mean by this, when I write this expression essentially in English in this way, what I mean by this is that there is this 4, and this is supposed to be multiplied by essentially the sum of 9 and 2. The sum of 9 and 2, of course, you know that it's essentially 9 plus 2, which is equal to 11. So I write essentially 9 times 2, and essentially because of the fact that I want essentially the 4 to be multiplied by this whole thing, I put this into these brackets, and then everybody knows that essentially by this expression I mean essentially this sentence in English, right? If I don't take essentially if I don't observe these rules, then there will be confusion essentially, and for example I write this expression over here, and then people might not know what I meant by this expression. So these are essentially things essentially like conventions that everybody has to follow essentially, right? And then basically based on the fact that I had this in mind, and based on that essentially I wrote essentially this expression, then essentially I have to take into consideration, I have to follow the exact same rules in evaluating this expression. Meaning that I say that, for example, that this is okay. So I have a bracket over here, and 9, actually this is plus 2. And 9 plus 2 is equal to 11, and 4 times 11 is equal to 44. And that's the answer that anybody would come up with if they were essentially following the exact same rules. And of course, in mathematics, we cannot have, I mean, when we have essentially a single expression, everybody is supposed to come up with the exact same answer. Otherwise, then there is going to be just confusion, and then mathematics cannot exist in the way that it exists anymore. So for the exact same reasons, basically for the exact same reasons, essentially I discuss essentially these rules over here that you're supposed to follow, right? Otherwise I never follow rules. I always emphasize basically understanding, right? Now, so having essentially all of these in mind, now let's take a look at a couple of expressions over here. So let's say that essentially we have a calculation, like for example 7 times 109, and 7 times 109, if you were to do the calculation, essentially you would write 109 essentially times 7, and then 7 times 1 is equal to 63. When there is a 0 over here, then you do not need to essentially write it as when you have a 0 over here. So normally essentially if it is for example 129 times 7, so if I substituted this 0 with a 2 essentially, so then if I want to do the calculation, 7 times 1 is equal to 63, so I put the 60 over here, or essentially the 6 over here, and then 7 times 2 is equal to 14. 14 plus 6 is equal to 20. So then I put the 0 over here and then the 2 over here, right? And then 7 times 1 is equal to 7, and that's a 930, right? And 129 times 7 is actually a 930, right? So then essentially in multiplication we always for example 7 times 9 is 63. I write the 3 over here, I put the 6 over here, and then add it to the next place value, and so on and so forth, right? But then when you have essentially 109 times 7, for example, so I write 7 times 9 is equal to 63. I keep the 6 over here, and then 7 times 0 is equal to a 0, and a 0 plus 6 is equal to 6. So I could just simply have written the 63 from the beginning over here, and then I don't have to bother about essentially the 6 over here, because essentially that's the thing that automatically happens. So when you see a 0 over here, 7 times 9 is equal to 63, you write the 63 over here. Of course the 6 has to be written essentially under the 0 as it is, right? And then 7 times 1 is equal to 7, that's 763. That's a 763, right? Now this calculation, you can do it in your head much more easily. You could say that essentially we have 7 times 109, and that's essentially 109 is essentially nothing but 100 plus a 9, right? So when I say essentially that's a 7 times 109, I could write it as 7 times essentially a 100 basically plus a 9, which is, as we discussed before, we said that essentially multiplication distributes over addition. So this is multiplication, this is addition, and so multiplication distributes over addition. So you distribute your 7 over essentially these numbers, and you write it as 7 times basically 100 plus basically 7 times a 9. Now 7 times 100 is the same thing as 700, and 7 times 9 is equal to 63. That's 763, which is the answer that we got over here, right? Now you can do this also in your head. You could say that basically 7 times 109 is essentially 109 is 100 plus a 9. So when you say 7 times 109, that means essentially 7 times 100 plus a 7 times a 9. So it's 7 times 100 is a 700, and 7 times a 9 is 63. So when you add them together, you get a 700 plus a 63, which is 763, right? Or you could actually use the brackets over here, as I did over here. So you could write this as essentially a 7 times, and instead of 109, you could write essentially 100 plus a 9, and that's, again, you can distribute. As you see, I have multiplication and addition. So multiplication distributes over addition. So you can write essentially 7 times 100 plus a 7 times a 9, which is the same thing as a 700 plus a 63, which is equal to 763, right? So these kinds of calculations essentially you can do very easily by using brackets, okay? And these are, of course, all different rules of algebra, okay? And well, I showed you essentially before why you can distribute. You must understand essentially why you can distribute. You just essentially in the big somewhere in the beginning of this video, I showed you essentially why you can actually do this distribution, okay? Now suppose that you have basically a more complicated calculation. For example, 102 times, for example, 103, right? Now this essentially, again, basically 102 is the same thing as essentially 100 plus a 2, right? And 103 is the same thing as basically 100 plus a 3, right? And so I could instead of essentially this calculation, I could write essentially 100 plus a 2 times basically a 100 plus a 3, right? Now this is still the same calculation that we had before, except that it's gotten a little bit more complex, basically, meaning that we said that essentially, for example, 100 times, for example, 2 plus a 5, for example, and we said that basically that multiplication essentially distributes over addition. So then we could write this as 100 basically times a 2 plus basically, and then the plus comes from here, and 100 times a 5, which is the same thing as essentially 200 plus a 500, which is the same thing as essentially a 700, right? And that's a 700 basically. Now instead of basically, now the exact, so this is the same thing as a 700. Now in the exact same way, what you could do is that you could, of course, make this calculation, you can make it a little bit more complex, the exact same calculation. Meaning that instead of 100, I could write essentially a 50 times 50. A 50 actually plus a 50, which is 100. And then I multiply it by 2 plus a 5, right? It's still the same thing, meaning that it's still this whole thing multiplied by this whole thing, and then there is essentially addition over here, and then there is multiplication over here. So still basically the essentially multiplication distributes over addition, right? But then, so then I could write this as essentially a 50 plus a 50 times basically a 2, and I have to put these in brackets, plus basically a 50 plus a 50, put these in bracket, times a 5 basically, right? And then basically I could again expand this, meaning that it's still essentially multiplication and addition. So then multiplication distributes over addition. So then I could say that this is 2 times 50, this is 2 times 50. So I write this as 2 times 50 plus a 2 times 50, right? And then I add to this, this is again multiplication distributes over addition. A 5 times 50, a 5 times 50. So 5 times 50 plus a 5 times a 50. And that is the same thing as, well, 2 times 50 is equal to 100. 2 times 50 is equal to 100. 5 times 50 is equal to 250. And 5 times 6 is equal to 250. So this is 100 plus 100 is a 200. And then 250 plus 250 is a 500. And that's equal to 700, right? So it's again the same 700, right? So then basically whether you have essentially 100, for example, times some number plus some other number, or if you have essentially some two numbers added together times another two numbers added together, it's going to be the same story. So then of course you don't have to go through essentially all of these steps. As long as you understand this, then you can say that, for example, you can say that essentially a 50 plus 50 times, you can say that essentially a 50 plus a 50 and multiply that essentially by the same thing, a 2 plus 5. I'm going to write this as, I'm going to say that essentially the exact same thing, meaning multiplication distributes over addition. So first I'm going to say that these two essentially are going to be, this is going to be multiplied by these two numbers. So I'm going to say 50 plus 50 actually times 50 times a 2, and then add to that 50 times a 5, right? And then again add to that. Over here now I have a 50 times a 2 and a 50 times a 5. A 50 times a 2 plus a 50 times a 5. And then I'm essentially 50 times a 2 is equal to 100. A 50 times 5 is equal to 250. A 50 times 2 is equal to 100. And a 50 times 5 is equal to 250, right? And that's essentially a 100 plus 100, that's a 200. So that's a 200, these two, and 250 and 250 is a 500, and that's essentially 700, right? So you don't have to, as long as you understand essentially what happens here, then you can just simply distribute basically, meaning these two numbers are added together multiplied by these two numbers are added together. Then you can just simply distribute 50 times a 2 plus 50 times a 5, then 50 times a 2, then 50 times a 5, and then add essentially all of those numbers together. So that's a 3 additions, that means you have 4 terms over here. So all of these are being essentially added together, right? So then if I come back essentially to my original problem over here, I have essentially 102 times 103. Now if I were to do this calculation by hand, I would have 102 times 103 and then multiply. So 3 times 102 would be 306. Put a 0 over here, and then 0 times anything is 0, so I will add another 0 over here, and then 1 times 102 is 102, and then add the whole thing together. A 6, a 0, a 5, a 0, a 1. That's 10,506. Now the exact same essentially calculation, I could essentially do it in a simpler way. I could say that essentially I will distribute multiplication over addition, right? And then there is another addition over here, of course. So then I'm going to say that this is essentially 100 times 100 and plus 100 times 3. So then I'm going to say that this is the same thing as 100 times 100 plus, and this plus essentially comes from here, okay? And 100 times 3. And then basically we have another addition over here. And now essentially I can distribute 2 over these two numbers. I can say essentially 2 times 100. I can add to this essentially the 2 times 100, and then again add to that the 2 times the 3. So that's going to be equal to essentially 100 times 100 is essentially a 10,000. 100 times the 3 is equal to 300. 2 times 100 is 200. And 2 times 6 is equal to 6. Which means that that's a 506. That's 10,506, which is the number that we got over here. Okay? Now these are, of course, important. You need to understand them. Later on, we are going to use them in algebra in more exciting ways, actually. Okay, and I, of course, like always, I advise you to essentially write these down. Once you essentially understand them in the video, once you know essentially how they work, you are actually supposed to write them down on a piece of paper and use actually your own hand. Use your hand, write them down on a piece of paper and go through all of these calculations. Okay, otherwise it's not going to stick with you basically. Now let's do another calculation over here, and that is basically 17 times basically 109. Now let's see how we can do this. So 17 actually basically to make essentially calculations easy, you always essentially want to write your numbers essentially in terms of 10, because essentially when it comes to multiplication, of course, because essentially 10 it's always very easy to multiply a 10 by anything, meaning that if you have, for example, a 12, when you multiply it by 10, you don't have to do any sort of calculation. You just write your 12 and then you add a 0 over here. That's 120. Suppose you have, for example, a 16 multiplied by 10, you will simply get 160. You have a 5 multiplied by 10, you will get a 50. And so when you multiply by 10, you just add a 0 and you don't have to do any calculation. And of course the same goes for any essentially any number, like for example like 10, 100, 1,000, or essentially a 10,000, and so on and so forth, because essentially they have essentially the only digits that these numbers have, they have essentially only 1, which means that essentially a 1 multiplied by anything is just the same number, so you don't have to do that really from the very beginning. And so the only thing that remains in the case of these numbers is the number of zeros. So anything that you multiply by 10, you will add 1 0. Anything that you multiply essentially by 100, you will add 2 zeros. Anything you multiply by 1,000, you will add 3 zeros, and so on and so forth. That's the reason why we express essentially all of these numbers in terms of 10 when it comes to multiplication. So then basically a 17, for example, you would write it as a 10 plus a 7, for example. Okay. And a 109, you would write it as 100 plus a 9, for example. Now you can do the exact same thing that we did before. You can just simply say that this is multiplication which distributes over addition, so you can distribute. And then you will start essentially with one of your numbers, you will do the distribution, and then you will come around to the next number. Okay? So what this means is that essentially we have 10 times 100, 10 times a 9, and then they are of course added together, right? So you would write essentially 10 times 100 plus essentially 10 times a 9. And then you will add to this essentially a 7 times 100 and a 7 times a 9. You will add to this a 7 times 100 plus a 7 times a 9. And this is then easy. So that's it. Essentially 10 times 100 is 1000. 10 times a 9 is 90. 7 times 100 is 700. 7 times 1 is equal to 63. Now that's 1000 and a 700. That's essentially 1700. And a 90 plus 63 would be what is a 90 plus a 63. So that would be the same thing as a 90 plus a 60 plus a 3. A 90 plus a 60 is equal to 150. And then we have a 3 essentially remaining. So a 1700 plus 150, that's 1850 plus a 3, which is the same thing as 1853. So that's basically your number over here. So I thought you might be able actually to do something with these, and of course along with all of these essentially we get to learn essentially algebra, which is of course a great and beautiful tool in and of itself. Hopefully in these courses I can show you I will be able to show you essentially the power and the beauty of algebra. It's really remarkable how it works. It's like it's really beautiful. Anyhow, I will end this video here, and then in the next video we will talk a little bit about Roman numbers. Thank you. Okay, so next we will talk about Roman numerals. In some contexts, essentially these numbers are used for essentially and of course you're supposed to be able to understand them, meaning that the number is basically written this way. For example, this is a 27, for example. So then you're of course supposed to understand all of these numbers, right? Now, the way that the Roman numerals works, the way that this system works, I think of course you can think of this as essentially as a number system. You can think of this as a number system, and basically in a number system essentially you have these different characters, or essentially the digits that essentially you use in this number system, meaning that for example in the decimal number system, which is essentially a base 10 number system, we have essentially all of these different characters, or essentially all of these different digits that can be used in the number system, and that is essentially 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's it basically, right? Now the essentially the good thing about the decimal number system is that it's essentially a positional number system. It's essentially a positional number system, and because essentially it's a positional number system, you can essentially all the numbers you could think of. It's possible to essentially create all of those numbers only using these 10 characters. Essentially 0, 1, 2, 3 all the way up to 9, that's only 10 characters. And then essentially these different characters, you put them in different positions, and that gives essentially, that contributes essentially to the value of the whole number. Meaning that essentially in the decimal number system we have basically the ones place value, the tens place value, the hundreds place value, the thousands place value, and you can just keep going with this. You get the 10,000, the 100,000, the million, and so on and so forth, right? And then basically if I put for example, if I put a 2 over here, that becomes essentially, because it's in the ones place value, it's a 2 groups of 1, which is just a 2. If I put the 2 over here, it's 2 groups of 10, so it becomes, the value becomes a 20. If I put the same 2 over here, it's 2 groups of 100, which is essentially a 200. And then if I put the same 2 over here, it's 2 groups of 1,000, which is essentially a 2,000. So essentially the same digit 2, when you use it essentially in different positions, it's going to give you essentially different values. And so of course for the same reason it's called essentially a positional number system, right? And because of the fact that it's a positional number system, then basically in the decimal number system essentially we have the idea of a 0, right? The idea of a 0 essentially has to exist in the decimal number system, because otherwise you wouldn't be able to make essentially all of these numbers. Meaning that, for example, I want to make the number, for example, 2000, right? So that's the ones place value, that's the 10, that's the 100, and that's basically the thousands place value, right? So then if I put essentially a 2 in the thousands place value, that essentially, that alone is going to be 2 groups of 1,000, which is a 2,000. But then of course these place values of course have to exist in the number. Otherwise if I just write a 2 over here, that would be just a 2 basically, and not a 2,000. So I have to be able to put something essentially in these place values so that this 2 has the value of a 2,000. And so for the same purpose essentially we use 0 in the decimal number system. We put a 0 over here, we put a 0 over here, we put a 0 over here, which means that essentially in the ones place value I have 0, I have nothing. In the tens place value I have nothing. In the hundreds place value I have nothing. But then in the thousands place value I have essentially 2 groups, which means that then the value of the number essentially is a 2000, right? So that's the idea of a positional number system basically. Now the Roman number system is not a positional number system, and then basically you have this idea of additive and subtractive principle in this number system. You have essentially of course the Roman, essentially the Roman, whatever you call it, let's call it essentially the Roman number system. It is of course you could say a primitive number system, but it is of course a number system, because essentially using the system you can create essentially all the numbers that you could think of. except that it's going to be a little bit it's not very easy to work with this number system, meaning that essentially for large numbers, then you could essentially, the number might get too long. You would have to do a whole lot of calculation to write something down, or essentially problems like that. Okay, so then basically, but then at the end of the day, the Roman of course here it's been called the Roman numerals, but I'm not very comfortable with the title. I would still call the whole system, I would call it essentially a number system. And then if this number system, we call it the Roman number system, it is of course a number system, because using, well, the system, you can essentially create all of these numbers. It's actually a complete system, but it's not a very comfortable system because it's not positional, and then you have to add and subtract things together to build all of these numbers. But it's still basically a number system. Okay, now in the decimal number system, we use essentially the Hindu Arabic. We use the Hindu Arabic numerals, and those are essentially the characters that we use in the number system in order to write our numbers down, which is essentially 0, 1, 2, 3, all the way up to 9 basically. These are called the Hindu Arabic numerals. Now in the Roman number system, essentially what we use is called essentially the Latin script alphabet, which is essentially nothing but the alphabet, or essentially a subset of the alphabet that we use in the English language, like the A, B, C, and so on and so forth, but only a subset of that, meaning that basically we would have essentially to write down 1, basically in the Roman system you would write an I. For a 2, then basically you would use essentially a combination of 1 and 1, you put it together. So, and then for a 5, for example, you would use a V. For a 10, essentially, let me take a look at, I need to cheat a little bit. For a basically for a 10, you would use an X. For a 50, you would use essentially an L. For a 100, you would use a C. For a 500, you would use essentially a D. And for 1,000, you would use essentially an M, basically, right? So that's the only, essentially, as I mentioned, you use only essentially a subset of the Latin script alphabet. So, and then basically you have only these, essentially the 1, the 5, the 10, 50, 100, 500, and 1,000, and then you can essentially put these together in different ways to essentially to create all the numbers that you want to create. Now the important thing about the Roman number system is that, well, since it's not a positional number system, then there has to be some way essentially to write your numbers down, basically, meaning that essentially in the decimal number system we write, for example, a 232, for example. This 2 is in the hundreds place value, this 3 is in the tens place value, and this 2 is in the ones place value. So then essentially automatically the value of this 2 becomes a 200, the value of this 3 becomes a 30, and the value of this 2 becomes essentially a 2. and then a 200 plus a 30 plus a 2 is a 232, right? Now in the ROM, so then of course the decimal number system is of course a positional number system, but then the Roman number system is not a positional number system. What it is that it works essentially based on the principle which is essentially called the additive principle. So essentially we have the additive principle here, and we have also essentially something in this number system. We have something essentially called the subtractive. We have the subtractive notation. Now what that means is that basically the additive principle means that essentially when you want to write a number, of course the only thing that you can use in order to write down your numbers would be essentially only these characters that you see over here, right? So then of course, because there is no place value essentially, or no positional system in this number system, essentially suppose that you want to write a 3. Then what happens is that essentially a 3 is essentially nothing but essentially a 1 plus a 1 plus a 1, and a 1 essentially is this I over here. So I will write essentially a 1 plus a 1 plus a 1, essentially put them together one after the other, and then we follow essentially the additive principle, meaning that when you're reading this number, you know that essentially that's a 1 plus a 1 plus a 1, so this number essentially is a 3 basically, right? Or essentially, for example, if you want to write a 6, for example. If you want to write, for example, a 6 essentially in this number system is essentially a 5. You cannot say that, for example, I mean, you might think that, for example, you would write a 1, essentially a 1 plus 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 a 1, and that would be essentially the same thing as basically a 1 plus 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 a 1. But then you can see that then it doesn't, I mean, it's just a whole bunch of ones put together. So the number essentially gets unnecessarily way too long basically. So what they do in this system is that essentially for a 6, for example, and this is a rule that has to be followed, of course, you have to write it essentially as a 5 plus a 1, which would be essentially a 5 would be a V, and a 1 would be an I. So then I write a V over here, and I write an I over here. That's a 6. Okay, that's a 5 plus a 1 is a 6. And well, in the exact same way, of course, you can write all of these numbers. For example, I don't know, a 15 would be, for example, a 10 and a 5, for example. So then if you want to write a 15, that would be essentially a 10 plus a 5, which would be essentially an X and a V, and that would be essentially a 15, right? Now that's all about the additive principle, which is essentially the principle that essentially puts the whole system together. Now about the subtractive notation, what that means is that basically about the subtractive notation is that suppose that, for example, you want to write a 4, for example, right? A 4 essentially in this system is not, you cannot write essentially a 1 plus a 1 plus a 1 plus a 1. That would be wrong. Okay, you cannot do that. So you have to essentially you have to write it as a 5 minus 1. And of course you know that essentially a 5 is a V, and a 1 essentially is a 1, is an I basically. So then now how do I do subtraction? in order to do subtraction, I will put essentially the v, which essentially represents a 5. I would put it over here, and then the 1, which is being subtracted from the 5, I will put it before the v. Okay, so then this essentially means that this one is being subtracted from this 5, which means that then of course a 5 minus a 1 is equal to a 4, right? Or for example, you know that for example a 10 is the same thing as an x, for example, right? So an x is a 10 basically. Now if you want to write a 9 in this system, it's the same thing as essentially a 10 minus a 1. And now you can guess essentially how you can do this. So you put it essentially a 10 over here, and then you subtract the 1 from it, and of course the 1 you have to put it on the left hand side of 10 so that it is subtracted from the 10, so that you will end up essentially with the 9, right? That's essentially how the whole system works. And in the exact same way, basically you can write essentially all the numbers that you want to write over here. And so that's essentially this system. Now let's go through essentially this text. Now this is essentially about the Roman numerals. This is the 1, 2, 3. So essentially you can see that a 1 is just an I, a 2 would be a 1 plus a 1, a 3 would be a 1 plus a 1 plus a 1, a 5 would be essentially this v, a 4 would be essentially a 5 minus a 1, a 6 would be a 5 plus a 1. You see, when the I is written on the right hand side, it's being added. When the I is written on the left hand side, it's being subtracted from the 5. A 7 would be a 5 and a 2, so you write the 5, and then on the right hand side you write a 2, meaning 2 ones basically. An 8 would be essentially a 5 and a 3, so you write a 5 and then 3 ones, all added together, that makes an 8. And then a 10 would be essentially just an x, and then a 9 would be a 10 minus 1, so you write your 10 and then you subtract the 1 from it, in that you write the 1 on the left hand side. So these denote essentially 1 and 2 and so on and so forth. And of course you can see that in this number system, it's just simply not necessary to have any of these we do not need essentially any such characters for a 0, because the 0 is already in the character itself, meaning that for example for a 10 you will use essentially this character over here, and then, well, the way that we think about the 0 is already in there, but then in the number system itself the 0 is just simply not necessary. Okay, so this is followed by, for example, if you want to write an 11, you would use essentially a 10 and a 1. A 12 would be essentially a 10 and a 2, and until you get to essentially a 10 and a 10, which is essentially 20, right? And these are essentially all the symbols that we discussed before. That's a 1, that's a 5, that's a 10, that's a 50, that's a 100, that's a 500, and that's a 1000. So now there are essentially some rules for this system, and I remember the last time that I was here, these rules have been formulated very neatly. So if a symbol is repeated, its value is added as many times as it occurs. So for example, a 2 is equal to, so essentially a 1, when you repeat it twice, that means that the value is added as many times as it occurs. So the value of this would be a 2. It's essentially when you when you repeat essentially a 10 twice, the value is, well, repeated twice, meaning that's a 10 plus a 10, which is a 20. If you repeat a 10 thrice, then essentially you have repeating a 10 thrice. That means that basically the value of 10 is repeated thrice, meaning 10 plus 10 plus 10 is a 30 basically. A symbol is not repeated more than 3 times, but the symbols V, L, and D are never repeated. So essentially you can, for example, to write a 30, for example, you would basically, you can repeat the symbol for 10 essentially 3 times, right? But then a symbol is, I mean, none of these symbols can be repeated more than 3 times. But then there is a couple of these symbols that can never actually be repeated, meaning not even twice basically. And one of those symbols is the symbol for 5 that cannot be repeated. L, which is 50, cannot be repeated, and D, which is 500, cannot be repeated. These three essentially you can never repeat. Next, essentially, if a symbol of smaller value is written to the right of a symbol of greater value, its value gets added to the value of the greater symbol. If the symbol of a smaller value is written to the right hand side of a greater value, that's essentially what we talked about when we were talking about essentially the additive principle. So we said that essentially when you want to use the additive principle, you will essentially write your 5 over here, and then when you put the 1 on the right hand side of it, the value of 1 is essentially added to the 5, which means that then this essentially becomes a 5 plus 1, which is equal to 6, right? Or basically, for example, for this number over here, you have a 10 and a 2. So then that's a 10, and then the 2, because it's written on the right hand side, it's added to the 10, which means that essentially a 10 and a 2 essentially becomes a 12. For this symbol over here, for this number over here, you have an L, you have an X, you have a V. So an L is a 50, right? An X is essentially a 10 and a V is a 5, so that's essentially 65, right? And of course you have to make sure that you understand that, for example, when I want to write a 65, I have to essentially from the left hand side, I have to start from the largest symbol that I have. So the largest symbol that I have is essentially a 50. Then after that, essentially the largest one is the 10, and then that's a 5. Otherwise, if you essentially mess this up, then you're going to get you essentially then the value of that smaller symbol is going to be subtracted from essentially from something in the number, and then whatever you get, essentially the number 65, you're not going to get. Okay, so you will always start with the largest symbol, which in this case, for example, is a 50, and then basically you will add the 10, and then you will add the 5, and then all of them essentially added together essentially becomes a 65. And then of course, if a symbol of smaller value is written to the left of a symbol of greater value, its value is subtracted from the value of the greater symbol. That's essentially what we talked about. For example, when you want to write a 4, you would write it as a 5 minus 1. So you would write the 5, and then you would write the 1 to the left hand side, which means that then the value of 1 is going to be subtracted from 5. Or essentially a 9 would be a 10 minus 1. So you write the 10, and then the 1 is written on the left hand side to be subtracted from 10. X50, for example, would be essentially L is a 50, and basically X is a 10, so that's essentially a 10 minus or essentially a 50 minus a 10, which is a 40. Or for example, a 90, for example, would be, so a C is 100, and x is a 10, so that's 100 minus 10, which is a 90, for example. Okay. Now the next rule that we have is basically that basically the symbols V, L, and D. V is a 5, L is a 50, and D essentially is a 500. So these symbols are never written to the left of a symbol of greater value. What that means is that, for example, we saw that when you wanted to write a 5, for example, you would essentially write it as 4 minus 1, which is the same thing essentially a 4 essentially. When you want to write a 4, you would write it as 5 minus 1, which is essentially, you would, of course, you know that essentially a 5 is a V. So you would write a V, and then essentially when you want to subtract a 1 from it, you put the 1 on the left hand side. And so essentially, since 1 is now placed on the left hand side, that means that the 1 is being subtracted. And then essentially in this system, essentially whenever you want to write, for example, a 30, for example, you see that you want to write, for example, 160, for example. So then you would write essentially 100. You would write essentially 100, which is essentially a C, right? And a 60 would be essentially L, which is a 50, and then X is a 10. So you see CLX, and then essentially in this number you can see that C has the greatest value among essentially all of these symbols. Then L essentially after that, L has the greatest value. And then after these two, essentially X has the greatest value. Which means that, as I mentioned before, in this system, essentially you start from the left, and then you start with the symbol of the greatest value, and then gradually essentially the next symbols that you write essentially will have essentially less and less and less value until you get to the end of the number, right? Meaning that the symbol that you write essentially on the left hand side over here will have the greatest value among all the symbols, right? And then the value is going to keep essentially gradually decrease and decrease and decrease until you get to the end of the number. So, or essentially, for example, over here, let's take, for example, the example of a 207, for example. If you want to write essentially a 207, so you know that essentially a 207 is nothing but essentially a 200 plus a 7, and that's the same thing as essentially 100 plus 100 plus a 7, and essentially a 7 is the same thing as 5 plus a 2, right? And of course we don't have a 2 in this number system, but we have 100, we have 100, we have a 5, so we will essentially write it as 100 plus 100 plus a 5 plus a 1 plus a 1, right? Now, which essentially means that essentially now to write down this number, I need essentially 200s. And essentially 100 is a C. A C, essentially the value of a C is 100. The value of a V essentially is a 5, and the value of a 1 essentially, the value of an I would be essentially a 1, right? So I need essentially 2 of these hundreds, so then I will have essentially a C, and then a V, and then a 1, and then another 1. Now all of these I have to put together, right? So then I have to, of course, start from the left hand side and move towards the right hand side. And when I start from the left hand side, of course I have to start with the largest values symbols that I have. The largest value symbols are essentially 100 and 100. So I put 100 over here and another 100 over here. So then 100 plus 100 becomes essentially 200. And we wanted to write essentially a 207. So then I put the 5 over here, which is still the largest value symbol that I have. And then I put the 2 2's over here, which means that then it becomes essentially a C, a C, a V, and a 2. And then that way essentially all of the symbols are added together. But you see that as I move essentially from the left to the right, essentially I'm starting from the largest value symbols all the way up to the smallest value symbols, right? Now if I make a mistake, for example over here, and write for example a C, and then put one of these ones over here, and then put the V and the which of course doesn't make much sense. But then what this means is that we have essentially this C essentially is 100, this another C is 100, the value of this 1 is subtracted from the 5, so this whole thing becomes a 4, and then this becomes a 1, and of course this is of course not the right syntax, but then the number essentially becomes a 205 essentially, which of course I could have written as a 100 and a 100 and a 5 essentially. I could have written this way. But you're not supposed to essentially write something on the left hand side of something else which has a larger value, and otherwise essentially if you did so, then the value of that smaller value symbol is going to be subtracted. Okay, so then now that we understand essentially about this subtraction, it says that the symbols VL and D, which is essentially the 5, the 50, and the 500, are never written to the left of a symbol of greater value. So as we saw, essentially when you write a symbol to the left of another symbol of greater value, the value of that symbol, which is smaller, is going to be subtracted from the value of the symbol of the greater value. Basically there is going to be subtraction, which means that essentially VL and D are never subtracted. Okay, and the reason essentially why this happens, is that essentially this system, the Roman number system, is essentially based on rules. Okay, meaning that essentially the decimal number system, we don't have rules in the number system. We just essentially have the different place values. We have the definition for those place values, meaning that we know that essentially the first place value is the ones place value, and then the tens place value, and then the hundreds, and so on and so forth. And then based on the value of the place value, whatever digit you put in there, that's essentially the value of that digit, and that's essentially it. There is no other rule essentially in the decimal number system. And of course we don't have any rules like, for example, you're not supposed to put a 5 over here or put a 9 over here or things like this. Essentially does not even occur in the decimal number system, right? But then essentially in this number system, it's because based on the additive principle and so many rules and regulations, then when you bring in essentially those rules, then you have to bring in essentially exceptions as well. And these are the exceptions. And the reason why that happens is that when you bring in essentially those rules, there is going to, eventually and inevitably, there is going to be numbers which look like essentially, which look like you're subtracting something from something else, for example. And then we have to make conventions that, for example, this particular number, we are going to write it this way so that there is no confusion. Or essentially that particular number, we are going to write it this way, and so on and so forth, right? So then and then essentially these are essentially part of the same rules, meaning that essentially, for example, if you subtract a V or an L or a D essentially from something in the number system, then you're going to essentially create all of these problems. The number is going to look like something else. There is going to be confusion, that sort of thing, basically. And of course, the symbol 1 can be subtracted from essentially 5 and 10 only, meaning that essentially the symbol for 1 can be written to the left hand side of 5, which means essentially 5 minus 1, which is equal to 4, and then 1 can be written to the left hand side of 10, which means that essentially 10 minus 1, which is equal to 9. But of course you cannot write, for example, something like, I don't know, for example, a 99. You cannot write it as a 1 and a C to mean essentially 100, for example, minus 1, which is 99, for example. This is wrong. 99, you have to write it in some other way. And then basically the symbol 1 can be subtracted only from a 5 and essentially a 10. Okay? And the symbol 10 can be subtracted from L, M, and C only, meaning essentially X, which is essentially a 10. You can subtract it from a 50 to make a 40. You can subtract it from a 1000 to make a 990, and you can subtract it from a C2 essentially to make a 90. Other than that, I mean, you cannot then essentially you cannot use it to subtract the 10 from essentially any other digits, basically, except for L, M, and C. You can use them. You can use it with essentially these three symbols, basically. Okay, so now let's take a look at essentially these numbers over here. Following these rules, we get, for example, a 1 is just a 1, a 2 is a 2, a 3 is a 3, a 4 is a 5 minus 1, which is a 4, a 5 is a 5, a 6 is a 5 plus 1, a 7 is 5 plus 2, and 8 is 5 plus 3, a 9 is 10 minus 1, a 10 is a 10, a 20 is a 10 plus 10, a 30 is a 10 plus 10 plus 10, a 40 is a 50 minus 10, a 50 is a 50, a 60 is a 50 plus 10, a 70 is a 50 plus 10 plus 10, an 80 is a 50 plus 10 plus 10 plus 10, which is 50 plus 30 is 80, a 90 is a 100 minus 10, and 100 is a C, essentially, just 100, right? Now let's write down essentially a couple of Roman numbers. For example, a 73 and 92. And okay, so basically we have two numbers, 73 and 92. And essentially to write these two numbers, it's simple. A 70 essentially is a 50 plus a 20, essentially. A 73 is essentially a 50 plus a 10 plus a 10, which is essentially a 70. And a 3, of course, is a 1 plus a 1 plus a 1, right? Now a 50 in this system, now the numbers as we discussed before, essentially you have essentially for a 1 you use an I, for a 5 you use a V, for a 10 you use an X, for a 50 you use an L, right? So far we have all that we need. Now, so then a 73 would be the same thing as a 50. So you start with the largest essentially largest value symbol, which is a 50, and then you add to that basically a 10, which is essentially a 10 like this, another 10, and then another 1, another 1, and then another 1, which would be essentially LXX111, and that would be essentially a 73. This must be 73. Now, in order to make sure that you've actually written the right number, now you can go to this calculator, and you see that this website is called the Calculator Soup. Usually you can find many good calculators on this website. And if I clear this, if I write basically 73, and it gives me LXX and triple I, which is a 73, and we got LXX and triple I, right? Now for a 92, essentially what you can do is that basically you see over here, a 90 essentially is essentially a 100 minus a 10, right? So you could write this essentially as a 90 plus a 2, which is essentially 100 minus a 10 plus a 2, right? And 100 essentially is a C, so you would write essentially a C as 100, and then you subtract the 10 from it, which means that essentially you put an X over here, which means that you're subtracting a 10 from the 100, and then you add to that a 2, which is essentially 2 ones. So this whole thing, when you put it together, becomes XC double I, and that's essentially your number. Okay. Now if you take a look at the calculator over here, a 92 is supposed to be XC double I. Okay. Now usually, of course, this number system, you don't use it for, I mean, you almost never actually use it to write the number 92. But well, of course, knowing this much about this number system, it doesn't hurt to know this much about the number system, of course. And then essentially the last thing that we have over here is that you want to write the numerals 69 and 98 essentially in Roman numerals. Let's do these two as well. So I have essentially the number 69, and essentially a 69 you can go for a 50 and a 10, if I'm not mistaken. So you can go essentially for a 50 plus a 10, that gives me a 60. This would be a 60. And for a 9, of course, I have to go for a 10 minus 1, right? So that should give me essentially 69. Of course, in the end, of course, you should always check your work to make sure that you haven't made any mistakes. But anyhow, a 50 essentially is an L, and then a 10 would be essentially an X. So then 10 would be added to essentially to the 50, and then basically over here 10 minus 1 would be essentially an X, and then you want to subtract the 1, so you put it on the left hand side. So this is a 9, this is a 50, and this is a 10. That should be a 69. So when I put all of these together, I get LX IX. That should hopefully be a 69. Now let me put this in my calculator here, which is essentially a 69. That is LXIX. That is correct. There is no problem there. Now the number basically 98. The number 98 is essentially, you have to know essentially how to write down the 90 first. And 90 essentially is 100 minus 10, right? So we will write this essentially as a 90 plus an 8, right? And then essentially for the 90 part, I'm going to write essentially 100 minus 10. That's the 90 part. And then for the 8, I'm going to write essentially 5 plus 3 basically, right? Now 100 minus 10 would be essentially a C. C would be 100. And then you want to subtract the 10, so you put the 10 on the left hand side, right? And then a 5 would be essentially a V. And you have to add 3 to it. So, and of course, you know that essentially a 3 is essentially a 1 plus a 1 plus a 1, right? So that would be essentially a 1 plus a 1 plus a 1, all on the right hand side, so that they are added to, not subtracted from basically the value of 5. And so the numbers should be essentially XC, V, I, and I. And if I take a look at the calculator, and the number is 98, it is XCV, that is the number. It is XCV triple I. Okay. Okay, so that's essentially a little bit of information about the Roman number system. Now this was the last basically section of this this chapter. So then essentially we are done with this chapter. Now of course we are still a long way away from calculus. We'll have to essentially work essentially video by video through essentially all of these chapters to get to essentially to make our way to essentially to calculus. Okay, so the next thing that essentially you will have to essentially you will have to continue this course with the next course, which is essentially on chapter 2 of the same book, which is on whole numbers. And essentially, in order to know exactly where to get this course, the easiest thing that you can do is that you can go to the essentially to the website, to the Great IT Courses website. I will essentially put the link to the website to essentially in the description of all of these videos. You can go to the website, take a look at the overview of all the courses, and then from there you can essentially choose the next course and then continue with the same. And hopefully before too long and in a very short amount of time, we are going to get to essentially we are going to get to calculus, and we are going to of course have a lot of fun along the way. I'll see you in the next video, and thank you.